Okay, dear students, again let's proceed to the workout part. So we have completed already the fill in the blank part. So under the workout part, the first question comes here and you are asked to check the validity of these arguments. So the argument says if Ethiopia is a country of 13 months of sunshine, then Ethiopia is naturally endowed country. It is not true to say that Ethiopia is naturally endowed or Ethiopia is a mountainous country. Therefore, if Ethiopia is not the country of 13 months of sunshine, then Ethiopia is not a mountainous country. So, you see, according to this argument, you are supposed to identify whether this one is a valid argument or not. So, before we determine the validity of this one, we have to first write the equivalent mathematical logic expression for this particular argument. Okay, so how many different sentences are written here within this argument? Let's see. The first one says Ethiopia is a country of 13 months of sunshine. So you may consider this as one sentence. So you may call this to be P. And let's proceed. It says Ethiopia is naturally endowed. There is also another saying about Ethiopia. So you may consider that as what? Second one. Call it Q. So Ethiopia is naturally endowed country. That is represented by proposition Q. Do we have other sentence about Ethiopia? Let's proceed. Or something else. Here it says it is not true to say that Ethiopia is naturally endowed. We have assigned that to be Q. Or Ethiopia is a mountainous. Look, there comes another sentence about Ethiopia. So Ethiopia is a mountainous country, so you may call that to be R. So we have here or Ethiopia, our beloved country, is a mountainous one. Yeah, right in that. So we do have now three different, sentences about Ethiopia. So after having all these premises, conclusion follows. Therefore, if Ethiopia is not a country of 13 months of sunshine, then Ethiopia is not a mountainous country, it says. So we are now here, we are now on the way to specify whether this is a valid or not. So we directly go to the way we should write this in a mathematical logic form. And to do that, look here, we have this. The whole saying of this argument can be easily written by, mathematical logic form as can be shown here. How is this written? Let me explain. It says P implies Q. So this is a conditional statement made by if-then. Do we have if-then here? Yes. Look, if it says, then what follows here? Then, in between if-then, P must happen. Yes, if Ethiopia is a country of 13 months of sunshine, so P is used, then conclusion follows. Ethiopia is naturally endowed country. We have related that to be P, so Q, so we have Q here. Then another sentence is going to come. It begins by saying it is not true to say. If it begins by saying it is not true, we must have negation here. Say that now, look, Ethiopia is naturally endowed, that is Q. Then here we have used the connector disjunction, or so here we need to use a symbol for disjunction. Then R follows as it is. Ethiopia is a mountainous country. R comes as it is. Having these two as premises, what follows is the conclusion. So whenever you see this word, therefore, hence, as a result, something like that, this is the one that is coming behind that is going to be the conclusion. So here comes the conclusion. Again, the conclusion is made by a conditional statement because it says if, and here we have then. So in between if and then, there is negation of P. Ethiopia is not the country of 13 months of sunshine, so have that negation P as it is. Then follows, Ethiopia is not a mountainous country, which actually is a negation of R. Look, this long argument can easily be written by this short mathematical representation. You see? So the question now is how can we, identify whether this is valid or invalid argument? So for this we have statement and the reason. So as usual, we have two premises here, so we have to accept these two premises as a true one because the definition of validity says that we have to accept the premises as true one, and we have to come to the conclusion and check whether the conclusion can be true or not. If the conclusion is 100% true, we can say that the argument is valid. But if there is a possibility of having at least one F, it will never be valid, rather it will be invalid. So now let's proceed. So let's directly begin from our premises. Look, P negation Q or R is true. The reason is because it's a premise. Premises are taken to be true. Okay. Not only this, basically p implies q is also a premise, so we'll consider that out there later on. But anyway, here, if negation of q or r is true, clearly q or r is false because of the definition of negation, the rule of negation. The rule of negation says that if the negation of a certain proposition is true, then clearly the proposition has truth value false. Then the rule of negation says so. And again here, rule of disjunction said that when you combine two simple propositions to make a compound proposition having false output, necessarily the simple propositions must have truth value false. So q is false, r is false. The reason is because of the law or rule of disjunction. Okay, this is disjunction. Basically, I said conjunction. Please correct this by saying disjunction. Okay, so q is false and r is false. Now what comes next is p implies q is true. Look at the beginning, p implies q is true. Reason? Because it's a premise. It's already given to us. You see, p implies q is true, but we know what q is. It is false. So p implies false is going to be what? True. And we knew rule of what? Implication. The implication said that if the conclusion is false, to make the compound proposition true, necessarily the premise must be what? False, right? So p has to be false. This is because of the rule of what? Implication, students. Rule of implication. So now we knew what p and what, students? R. So if we knew p and r's truth value, we can determine what this is going to be, because the conclusion is expected to be determined. So from this, the following can follow. Negation of p implies negation of r is going to be true. What is the reason behind that? Because if p is false, this turns to be true. And if r is what, student? False, negation of r is true. True implies true makes true. So for, you see, the premises having truth value true, we obtain the conclusion true. So this shows you that the argument is a valid argument. I hope you have understood a very simple question. Now, having this, next is this one. It says, using a principle of mathematical induction, prove that x minus y is a factor of x to the power of n minus y to the power of n. This is true, basically. So whatever two different natural numbers you may take, you see the difference of the two is a factor of, you see, the difference of their exponents having the same what? Exponent natural number n. So using mathematical induction, I'm going to show you how this is true. So here comes the solution. Let p of n to be x minus y is a factor of x to the power of n minus y to the power of n. So now what follows is, you see, first step. We need to check the first step. And since this is asserted for the set of natural number, we have to check for n is equal to 1. So for n is equal to 1, you directly substitute 1 in place of n. X minus y is a factor of x to the power of 1 minus y to the power of 1, which actually is x minus y can come. And everyone agrees that x minus y is a factor of x minus y. Remember, you see, is a factor of itself because we do have a multiplier 1 for it. So this is a true saying, so we accept that. Had this been false, you see, we would have stopped here. No need of proceeding to the next step. But since this one is true, let's go to the second step. Assume that this works or holds true for up to a certain natural number k. You see, we don't know what this k is going to be exactly, but assume it works up to what? A certain natural number k. That is to say, p of k is true. P of k is x minus y is a factor of x to the power of k minus y to the power of k. Assume that this is true, student. This is true. P of k is true. Or accept that this is true. You see? So when we say that x minus y is a factor of x to the power of k minus y to the power of k, we can write that as x to the power of k minus y to the power of k as t times x minus y. Because we are accepting that x minus y is a factor of this one. If that is so, for a certain integer, you see, t, we can have this. See? We can have this. Now our next step is to assure the trueness of this one for, you see, n is equal to k plus 1. For n is equal to k plus 1, that is to say, you see, p of k plus 1 to be true. P of k plus 1 is nothing but it is x minus y is a factor of x to the power of k plus 1 minus y the power of k plus 1 is true. Simply put k plus 1 in place of n, nothing else. Are you able to show that this is true? If you are able to show this, you are done, students. So in order to prove this using the second step, now what you need to do is you have to just have some sort of steps over here in such a way that you could use step 2. Okay, step 2. So this can be done as you see. X to the power of k plus 1 minus y to the power of k plus 1 is equivalent to, look here students, x to the power of k plus 1 is nothing but it is x times x to the power of k minus y to the power of k plus 1 is y to the power of k plus 1. It is written as it is. But look here, what is done here is these, see, middle terms are added. Basically, these middle terms can cancel each other. I intentionally added these two in order to have this expression, student, x to the power of k minus y to the power of k, because whenever you are doing or applying this principle of mathematical induction, you need to create a mechanism where you can apply step 2. Okay, so for this sake you need to have negative and positive expression, identical, terms that can cancel each other, can be, you see, used in the middle, no problem. But here what is happening here is the following. Take x to the power of k as a common out. Look, x to the power of k as a common out, so as you are doing so, x minus y can remain, as you see. You see? And here let you take y as a common out, x to the power of k minus y to the power of k can come. But you can ensure y times y to the power of k is y to the power of k plus 1. And the product of these two makes this. X to the power of k times x is x times x to the power of k, and minus x to the power of ky. Right, we are. So look, student, here now. Here, x to the power of k minus y to the power of k is a multiple of x minus y, because it has been said here, you see, in step 2. So this is, you see, a multiple of x minus y, or x minus y is a factor of this. We already have x minus y. So if we do have x minus y, and again x minus y here, we can take x minus y as a common out. And then we can have, you see, this being a multiplier of x minus y, you see, as you see. So already x to the power of k minus y to the power of k is assumed to be t times x minus y, so I just use t times x minus y. So you can take x minus y as a common out, then a certain expression can come here. So this assures you that, you see, p of n is true. Why? Because p of n is true for n is equal to k plus 1, because we obtained that this x to the power of k plus 1 minus y to the power of k plus 1 is a factor, a multiplier of x minus y, or x minus y is a factor of this expression. So step 3 is true. Hence, because of step 1, step 2, and step 3, and the concept of principle of mathematical induction, one can conclude that, you see, by principle of mathematical induction, the given statement is true.